All right, let's get started. So welcome to another lecture as part of our ME 6151 Computational Heat and Fluid Flow course. So in today's lecture, we're going to kind of extend the simple algorithm on collocated grids for unstructured meshes, right? Essentially, this is the ultimate thing that we wanted to do because in order to be able to solve fluid flow equations on either unstructured meshes or on non-uniform meshes, we have kind of had a motivation that the collocated grid approach would be most suitable. Okay, so essentially we kind of come back to this picture where we have a cell which is sharing its faces with three other cells. Okay, so we concentrate on the primary cell, that is C0, and we have a neighboring cell C1 with face F here, and the line joining C0 and C1 would be E xi, and the unit vector along the face would be E eta, and then the face normal that is pointing outwards from the cell would be AF bar, and we also denote a unit vector of this face normal using n cap. Okay, so that's the idea here, and then we have our x and y coordinates which are the Cartesian coordinates as usual. Okay, so in the simple algorithm we are going to store essentially both the x component of velocity and the y component of velocity as well as pressure all at the cell centroid C0, right? And similarly we are going to store a similar Cartesian components at C1, C2 and all other cells. Okay, so that is the idea. Now if you look at the momentum equations, we had in the x momentum equation we had minus partial p partial x, so that was minus I dot grad p, and in the y momentum equation we had minus j dot grad p, that was minus partial p partial y. Okay, so we had used these things. We have integrated it on a particular control volume, and then we have also invoked the gradient theorem, right, and then converted them into a surface integral of the pressures, right, and the essentially multiplication of PF times AF over all the faces. Now either these terms can be treated in that fashion using gradient theorem, where the minus the grad p dv or the control volume can be converted into a PF times AF bar, or alternatively it can also be taken, this can also be treated similar to a source term, where grad p can be represented by using the cell centroid value, that would be grad p0 times once it is constant you can integrate this over the finite volume, that would basically give you delta v naught. Okay, so both these expressions are equivalent. So we are going to for now use this in the formulation, okay, instead of what we had used before in the context of the Cartesian meshes. Okay, all right. So then essentially what we can do is we can once we convince ourselves that the pressure gradient term can be written as minus grad p0 delta v naught, then we can concentrate on the cell 0 here, and we can write the x and y momentum equations in the discrete form for the cell C0. Okay, so that's basically going to give you your because it is cell 0, instead of APUP we have written A0U0 equals sigma NB UNB minus I dot grad P0 delta V naught. Remember in the previous lectures this was a kind of coming out to be, after integration this was coming out to be, because there is a I dot here, we got basically if it were let's say a collocated approach, then we got something like P west minus P east, right? Essentially because of the minus we kind of absorbed it, but now because we are leaving grad P0 as it is, we still have this minus coming into play. Okay, so that is what we have to keep in mind. This minus is associated with this grad P0, and in the previous lectures this minus was not there because that was absorbed into the when we have written the pressure as a summation of the faces. Okay, plus we have some source term, that is B0. Now to distinguish these coefficients we have included a superscript u for A0, A and B and B0. Okay, so let us call this equation 1, and similarly we can write an equation for the y component of velocity, that is for V0, which would be A0 V0 equals sigma NB VNB minus j dot grad P0 times delta V naught plus B0 V. Okay, so again essentially these coefficients might be different from the coefficients of the x momentum equation, As a result, we wrote V to distinguish this, right? Essentially, we have A0V, V0 equals sigma n B, V and B with V and so on. Let us call this Y momentum equation as equation number 2, okay? So we know how to discretize these two equations and solve for them for a known guessed pressure field, okay? Because you know how to calculate the gradient, this can be calculated, and essentially this will, A and B's will have components of convection and diffusion, and you know how to calculate the central coefficient, that is AP, and essentially we know how to solve for equations 1 and 2 for a guessed pressure value. Alright, now what comes next is basically we need to now come up with an equation for the phase velocities, right? We need to come up with a phase velocity because these velocities on the phases will be used in the discretization of the continuity equation, okay? So as a result, let us look at an equation for obtaining phase velocities, okay, especially in the direction that is normal to the phase, okay, that is in the n cap direction. We would like to get an expression for the velocity which can be used in the continuity equation, okay. So now let us define the phase normal vector, essentially a unit phase normal vector. Phase normal unit vector can be defined as n cap equals AF bar upon magnitude of AF, right? That is basically constitute a unit vector. That means this n cap can further also be written into its Cartesian components as I cap nx plus j cap ny, okay, where nx and ny are the x and y components of the unit vector that we would obtain, and this will be different for each phase, okay, but this can be computed and stored at one place. All right, then using the two equations we have, that is equation 1 and equation 2, we can also write an equation for the velocity u0 in the direction of n cap, okay. That means this u0 is different from this u0, okay. This u0 is the x component of velocity, v0 is the y component of velocity. Now we are writing for cell 0, we are writing an equation in the n cap direction, okay. We are writing the momentum equation in the n cap direction. We already have it in the x direction and y direction, so we can of course write an equation in any other direction, right, using these x and y equations. So that equation would be, of course we will see how to calculate these coefficients, but that equation would be a0n u0n equals sigma a n b u n b n minus, instead of I dot and j dot you have n cap dot, because this is in the direction of n cap, in the direction of the phase normal, dot grad b0 delta v naught plus b0 n, okay. So that's basically is a momentum equation for cell velocity, for c0 cell velocity in the direction of the normal. So basically in this direction we have written a component of momentum equation in this direction, okay, from the equation we have in the x direction and the y direction. All right. So now how do we calculate, of course, a0n and a_n and b0n? We basically already have these two. Essentially we have to multiply n with nx with this, ny with the second equation, and then somehow obtain what is a0n, okay. So that's what we would do. So a0n would be, you have a0u u0 and a0v v0 if you form a vector which is basically for the I cap component and the j cap components. Then you basically take a dot product with the n cap, and then you divide. You know that the velocity in the direction of the phase normal would be u0 bar. This is basically I naught u, I hat u naught plus j hat v naught. If you take a dot product with n cap, you are going to get a velocity in the direction of the phase normal, right? This is basically nothing but, this is what? This is your u0n, right? u0 bar dot n cap would be your u0n, right? Essentially this is nothing but your u sub 0 hat cap n, right? Not hat, essentially to the power superscript n. Okay, that means we already have a0 u0 and a0 v0, this entire component divided by u, that's going to give you the a0n, the coefficient here, right? Similarly, a and b can be found by taking components of these two, and b0n can be found by taking components of these two, right? So that means we can of course calculate all these coefficients and write a discrete equation in the direction of the phase normal for the velocity at the cell centroid C0, okay? Alright, now once we have this, can we divide this entire equation with a0n? Yes, we can. So if I do that, we are going to be left out with u0n on the left hand side. That's basically u0n equals On the right hand side, we have sigma a n b u n b plus b0 all at in the direction n divided by a0 n, that is this coefficient coming here, minus we have n cap dot grad p0 times delta v naught, right? That's basically this component, this candidate divided by a0 n, okay? That is nothing but your delta v naught by a0 n times n cap dot grad p0, okay? So again, we can of course denote this using some u hat. So this is some u hat n. This term is basically similar to your d terms that you have written before, right? You remember in the equations for the Cartesian x and y discrete momentum equations, we had something like 1 by a east, right? That we called as d east. Now that 1 was coming because of there was the volume was coming out to be getting cancelled out. Essentially, you have delta v naught as the volume here, right? So that's why you got delta v naught by a0 n. So this is similar to your d term, okay? So we will not substitute it at the moment. We will leave it as it is. Of course, we can rewrite this momentum equation for the cell velocity in the direction of the phase normal as u0 n equals u0 n hat plus or essentially minus delta v naught by a0 n times n cap dot grad p0, okay? So this is basically, if you know, this is the momentum equation for C0 cell velocity, right, in the phase normal, right, direction, right? Basically in the direction of phase normal, that is in the direction of n, what will be the velocity component, that is un, in the for cell C0, okay? So that's what this is. This is basically momentum equation for cell 0 velocity in the direction of the phase normal, okay? That is u0 n equals u0 n hat minus delta v naught divided by a0 n times n cap dot grad p0, okay? So let us call this equation 4. Then of course we can write a similar equation for the neighboring cell, that is basically C1 cell, right? So because these two cells share a common phase and that common phase has one particular n cap direction, we can write a component of velocity that is in this direction, a momentum equation, and similarly for the velocity components here we can find a velocity component in the direction of n cap and write a momentum equation, right? So if we do that, essentially do the same process again for cell C1, which is also sharing the same phase with the cell C0, then what we get is essentially the same equation with 0 replaced with 1, okay? So what we get is u1 n equals u1 n hat minus delta v1 upon a1 n times n cap dot grad p1, okay? Let us call this equation 5. Now this is basically, if you try to connect to the previous Cartesian equations we had, this is more like an equation for up and this is more like an equation for u capital E, right? Now we are using p and capital E to calculate little e, right, the phase value. That's what we do here as well. We want to essentially find the velocity on the phase, okay? Now if you assume a uniform mesh, we can take an arithmetic average, so that will be, if you have an arithmetic mean, that will be uf bar would be equal to u0 n plus u1 n by 2. This is basically similar to u east, u little e equals up plus u capital E by 2, right? Of course, if you don't have a uniform mesh, then you know you basically have to use grad u0, grad u1 and the corresponding delta r0, delta r1 and calculate what will be the phase values, right? Or else you can use some kind of a, if you are dealing with Cartesian mesh but with non-uniform mesh, then you would get some factor here, right? You would get f times u0 n plus 1 minus f times u1 n and so on, where f would be calculated based on the distance between the corresponding cell centroids and the phase centroid, right? So that we know how to do. So for now, without loss of generality, we will assume that the mesh is this kind of uniform, although it is unstructured. So it will be kind of simple for us to do. Okay, then what we can do is we can substitute for u0 n and u1 n from these two candidates, right? This is basically up and u capital E. Substitute these two, that is substitute for these two in this definition. So this is basically your arithmetic average or linear average, right? So linear interpolation. That means what you have is uf bar equals, if you substitute for u0 n in terms of u0 hat and this quantity and u1 hat and this quantity, what you get is you get u0 hat plus u1 hat by 2 minus, you have these two quantities which are added up and then multiplied with the 1/2, right? Essentially that's what you get. Essentially uf bar equals u0 n hat plus u1 n hat upon 2 excuse me, minus 1 by 2 times delta v0 by a0 n times n cap dot grad p0 plus delta v1 by a1 n times n cap dot grad p1. Okay. Now let us call this entire thing, this is half of this entire summation, u with a new value, okay, that is represented on the face as delta vf by af n times grad p dot n, where grad p bar is basically a face value of the pressure gradient. Okay, grad p bar would be some combination of grad p0 and grad p1, and delta vf would be face value for v0 and v1 volumes. Similarly, AFN would be some face value for C0 and C1 cells. Okay, so that means what we get is UF bar equals U0 n hat plus U1 n hat upon 2 minus, including this half, we are calling this as minus delta VF by AFN grad P dot n cap. Okay. All right. So this is basically your arithmetic average, right? This is your arithmetic average. That means we still have on the left hand side UF bar is basically equals U0 plus U1 upon 2, right? So this is basically this value, and then we have divided by 2, right? So we have, so this is what we have for UF bar, right? In terms of hats, this is what we get: U0 hat plus U1 n hat by 2 minus delta VF by AFN grad P bar dot n, right? So if I send basically, so this is your arithmetic average, but what we want to do is we have to find a momentum interpolated average, right? We want to use momentum interpolation. That means this pressure gradient we have to subtract this quantity and then add an adjacent pressure value. Okay, so but unfortunately here we already have a minus, so subtraction means that you are doing a minus of minus, so you are doing a plus. Okay, so again we will not work with u0 hat u1 hat here, we would like to work with u0 and u1. Okay, that means for this quantity we have to subtract this minus quantity and then add a quantity that represents an adjacent pressure. Okay, so that means I can write I would not write uf bar anymore, because uf bar denotes an arithmetic average. I will just write uf, which will denote a momentum interpolated value. That is nothing but your u0 n, okay, these are all n's, okay, these are all n, plus u1 n by 2, and then we subtract off this quantity, that is subtracting minus of this guy would be basically plus, right? Or else you can think of it as sending to the left hand side, right? You remember in the last lectures we had we subtracted minus of this quantity and then added the adjacent pressure on both sides, right? So you can also think of it like that, because there is already a minus. When you subtract it off on the left hand side direction, what you get is a plus. You get a plus delta VF by AFN times grad P bar dot n. Okay, and then you, so this is subtracted and then you add. So when you say add, you already have that minus in there, right? Because we didn't use the expansion for grad P. And then you add the adjacent pressures, right? So now adjacent pressure, this is where we would add it as a d times, that is basically delta VF by AFN times partial P partial n on the face. Okay, so this is your subtract the non-contiguous pressure gradient and then add the contiguous pressure gradient. Okay, so this may require you to basically you may have to go through this again and double check, okay, that this is correct. Okay, so whatever I have done here, you basically have to just double check it is correct. You just have to make sure you understand it. Fine. All right, so essentially what we have done is we have subtracted off minus delta VF by AFN grad P dot n and added on both sides, and added this quantity, that is minus delta VF by AFN partial P partial n F on both sides. Okay, and we are not working with hats anymore. We are working with, for now we are working with the original values. Okay, that means the u0 and u1. Okay, now this uf is our momentum interpolated phase value. Okay, so this is our momentum interpolated phase value. Now once you have the momentum interpolated phase value, where would you use this thing? You will use this in the continuity equation, right? So we need this in the continuity equation, because only then continuity equation will not support checkerboarding. Then we don't care if the momentum equation supports checkerboarding, because as one of the equations are not going to support it, it is not going to be there in the final converged solution. Okay. All right. So then, of course, we did not introduce how do we calculate the average values that we have used here, right? That we have said these two would be represented using some phase values. Now, this is one particular way of doing things. Okay, so there are several ways of, in fact, representing this interpolation. Okay, so we are using one particular way. That means we are using a arithmetic average, where we are saying grad P on the face, that is grad P bar, would be equal to arithmetic average of the neighboring cells, that is grad P0, grad P1 by 2. Similarly, the coefficient AFN that we basically got here would be, we say again, it's an arithmetic average of A0n and A1n, and the volume value, kind of a representative volume value for the face that shares two cells, we will again take it as delta V0 plus delta V1 by 2. This is not going to cause much of a difference, but there are several ways of doing this thing. Okay, you can also use a scaling factor based one, or a linear interpolation and things like that. Okay. All right, then if we go back and look at this equation, what we have is UF equals U0n plus U1n by 2, plus we have this delta VF by AFN common in these two terms. So if we take it out, we have delta VF by AFN times n cap dot grad P bar minus we have partial P partial n. Okay, so that means this is our non-contiguous pressure and this is our continuous pressure, right? Adjacent pressure term. Now what do we wish to do? We wish to do essentially, we want to represent this pressure gradient in the direction of the normal to the face, that is partial P partial n on the face F, using the cell centroid values. But we know that in general for an unstructured mesh, this gradient, right, cannot be, that is in the normal direction, cannot be just simply represented using the cell centroid values. You would get two gradients, one in the xi direction, one in the eta direction. You remember, you get these quantities basically in the context of diffusion equation for unstructured meshes. We got A dot A by A dot xi, right? Similarly, we got A dot xi, A dot A by A dot xi times xi dot en. So similarly, we get these two components. One is the primary gradient and the other one is the secondary gradient. Okay. Now we know that the primary gradient can be expressed as P1 minus P0 by delta xi, whereas the secondary gradient term, if we don't have a particular way of solving it, then what we can do is we can express this entire secondary gradient as the total minus the primary gradient, right? So if I somehow know the total gradient on the face, that is grad P bar, then this entire secondary gradient can be written as total minus the primary gradient. That means n cap dot grad P, this is the total total gradient on the face, right, minus we have the primary gradient, right? That's basically n dot n by n dot xi, grad P dot xi. Okay, now what you have to pay attention here is that the grad P bar, this is somehow known. Okay, so that is the idea here, right? We have gone through this discussion before in the context of diffusion equation, so we will not again go in detail here. But of course, now we have replaced the secondary gradient as total minus primary. Now what do we want? Essentially we want n dot grad P minus partial P partial n F. That's what the quantity we are looking for. That means from here, from this equation, I can write n dot grad P minus this guy, that is if you bring this quantity to the right hand side and send these to the left hand side, then what you get is n dot grad P bar, okay, there is a bar missing, minus partial P partial n F, that is essentially this quantity, equals, what does it equal? It equals basically your n dot n by n dot xi, that is common between this term and this term, and it equals grad P dot xi minus P1 minus P0 by delta xi. Okay, so that means we can replace for this quantity that is right here with grad p dot xi minus p1 minus p0 by delta xi. Okay. Now you see there is a difference between these two. This is not equal to 0, right? Because p1 minus p0 are the cell values, and grad p bar is a gradient of pressure evaluated on the face. Okay. So this is not 0. Okay. All right. So that we understand. That means if we plug in back into the UF equation, then what we have is you have u0n plus u1 by 2, u01 plus u0n plus u1n by 2 plus delta Vf by AFN, and we are replacing this quantity, that means delta Vf by AFN, by replace this quantity with this, that means what you get is n dot n by n dot xi, and you multiply this with delta xi, then you have delta xi in the denominator. Then what you have is grad p bar dot xi delta xi minus p1 minus p0. Okay. All right. Now we got a very long expression for what is this one? This is basically momentum interpolated phase value. Okay. This is basically your momentum interpolated phase value, for which we got a big expression. But nonetheless, we can rearrange this thing. We can write this as u0n plus un by 2 can be written as uf bar, right? Basically this quantity is your arithmetic average, right? So this can be written as uf bar, plus we have delta vf by afn times n dot n by n dot xi delta xi times this quantity minus this entire quantity times p1 minus p0. Okay, so that's what we have. Now if you denote this entire quantity which is the same for both as some df, so that is delta vf by afn times n dot n by n dot xi delta xi as some df. Okay, this is similar to your d east or d west in the Cartesian context. Then what we have is you have uf equals, we can simplify this entire expression as if this is df, then this uf bar plus this entire quantity can be written as uf cap, plus we have df times, so if you want to get rid of this minus, I would switch the p1 and p0, so we say p0 minus p1. Okay, where of course df is this quantity, delta vf by afn n dot n by n dot xi delta xi, and uf hat would be equal to uf bar plus df times this quantity, that is grad p bar dotted with xi times delta xi. Okay, so we have now simplified it by defining two coefficients, that we call it as uf hat and df, and we got this equation 7, which is basically similar to the equations that we got before, right? So basically this is more like your u east equals right, u east hat plus d east times something like pp minus p east, right? Something like this, you remember? So this has very good resemblance to the Cartesian components. So what we have is uf equals uf cap plus df times p0 minus p1. So what you notice is you got a pressure difference of the neighboring values, that is p0 and p1 and you got hat velocities, and here we don't have the superscript, but uf itself denotes the velocity vector on the face in the direction of the face normal. Okay, so this is already in the direction of n, so we have not been writing this, right? So that means if you multiply this with the area magnitude and you multiply with density, then you are getting the flow rate already. Okay, so that we can use this directly in the continuity equation. Okay, all right. So then we have now computed a value for the velocity in the direction of the face normal from momentum interpolation with the help of adjacent pressure gradients. Let's call this as equation number 7. Okay. So once you have this, the final step is basically to come up with a pressure correction equation. Pressure correction equation is basically, where do we start for that? We start off with the continuity equation. So the continuity equation would be, if you have several phases, then the continuity equation is sigma ff equals 0, right? Where your ff is rho f, this is a kind of a flow rate, that is rho f times af times uf, right? If af is always pointing outward, so if uf is going out, this quantity would come out to be positive. If it is coming inside, this will automatically come out to be negative. Okay, so that will take care of the plus minus signs. Then what we have is then the continuity equation is basically summation over f sub f. So this is your continuity equation, right, for the cell 0. Okay, Then what do? We split this into a star value and a prime value. So we can write this as ff star plus ff prime equals 0. Then of course the ff prime, so the stars are known values, these are the guess values that are known. Of course they don't satisfy continuity equation, so this sigma ff star would not be equal to 0, but ff primes is what we want to express them as in terms of uf primes, right? So now we need an expression for uf prime. How do we get it? We basically get it from the momentum interpolated value. So if you have uf, if you want to take a prime here, basically subtract this off from the star equation. So then what you have is uf minus uf star, that will give you uf prime. So this equation, equation 7, if you rewrite for primes, what you get is uf prime equals uf hat prime plus df times p0 prime minus p1 prime. Okay. So this is what we get. Again, keeping with the simple approximation, the contribution of the neighbors is neglected. So what you get is uf prime equals df times p0 prime minus p1 prime. This is more like your p east prime minus pp prime minus p east prime, right? Okay. Then you plug in, okay, there is a star hat missing here, so that means your ff prime, right? Ff prime equals rho f af uf prime equals rho f af times df times p0 prime minus p1 prime. Essentially substitute for uf prime from the equation above, then you got an equation in terms of pressure corrections for flow rate correction, right? So this is basically flow rate correction in terms of pressure corrections. Okay, fine. Then what do? You basically substitute for ff prime in terms of pressure corrections into this equation and rearrange them into our favorite standard form. That's basically, this is our standard form, which is basically APPP prime equals sigma NBP NB prime plus B. Okay, of course you can write this as A0 P0 prime, either of them is fine. Then what we have is A and B would be equal to rho f df AF, right? This the multiplication coefficient for P1 prime, that's your A and B, and there will be the same contribution to the cell PP or P0. So as a result, your AP would be summation of all the neighboring coefficients. That means AP equals sigma A and B. Then your B term would be, because it goes to the right hand side, it will become minus ff star sub f. Okay. So this is again basically the amount by which the star flow rates does not satisfy continuity equation. Okay. So that's what we have. Then we basically solve for the pressure correction. Once you have the pressure corrections, you basically put them here and calculate what is the velocity corrections and flow rate corrections. Once you have the velocity corrections for the phase velocities, you go back and correct your phase velocities as well with the corrections. Okay, so that's what we do. So once you have the pressure corrections, you correct the cell pressures. P0 equals P0 star plus P0 prime. UF prime equals, so basically obtain the velocity corrections. UF prime equals df times P0 prime minus P1 prime. Of course, see, this is for one phase is what we have written, right? So this is for one phase. Now this has to be done for every phase that we have, right? That means P0 prime minus P1 prime, P0 prime minus P2 prime, and so on, right? For each of the UF1 prime, UF2 prime, UF3 prime, and so on, depending on how many phases that the cell C0 has. Okay, all right. Similarly, once you have the phase velocity corrections, you can essentially correct the phase velocity itself. That is, UF equals UF star plus UF prime, right? So this basically would be correct the phase normal component of velocity, okay, which will be later on again used in the continuity equation. Okay, and then you have PF prime. This is the correct the phase pressure as the arithmetic average of the cell pressures, P0 prime plus P1 prime by 2. Now, in order to improve convergence, we not only kind of correct the phase pressures, but also correct the cell pressures. So cell pressures are U0 prime equals. So if we follow a similar approach, instead of delta Vf by Af, we have minus delta V naught by A naught n times, here I am using, similar to this, I am using a, you remember we get this sigma Pf prime AF, but because this is X component, it's only the, if you have this I dot P of AF, only the AX component survives. Similarly, V0 prime would be equal to minus delta V0 by A0V sigma PF prime AY. Okay, so this is basically correct the cell wall velocities to improve convergence. Okay, this is basically similar to the phase velocity corrections that we have done above. Okay, purely to improve convergence. Okay, so once you have this thing, then essentially you know what is the phase velocity correction. Then the cell velocities can be updated as u0 equal to u0 star plus u prime 0. Similarly, v0 equals v star 0 plus v prime 0. Okay, then basically you update your new guess u star 0 would be your u0, and v star 0 would be your v0, and then you go back to the previous step, that is basically solution of the discrete momentum equations, this ones, right, equation 1 and 2, discrete momentum equations with the new guess values. Okay, so that is the idea. It's basically very much similar to what we have done for the collocated mesh on a Cartesian arrangement. Okay, and of course you know how to solve for the momentum equations 1 and 2 anyway, right? That's basically similar to the general scalar transport equation. Okay, so that kind of finishes this chapter on the computational fluid flow equations, wherein we have seen the staggered mesh simple algorithm and the simple algorithm on collocated meshes, then simple algorithm extended on collocated meshes to unstructured meshes, and everything. Okay, so the only thing remaining now is the multigrid method in chapter 5. Okay, so we'll be taking maybe 2 to 3 lectures, and then kind of motivate for why we need to go for a multigrid kind of method, and what is the need for it, and how does the multigrid methods work. Okay, so that's probably another 2 to 3 lectures maybe, and then we should be able to wrap up the syllabus. All right, so I'm going to stop here. If you have any questions, do let me know through email. Okay, thank you. Talk to you in the next lecture.